I enjoy talking about the exponential function. If you came through the 101 class, you have seen this before, but we're going to do it at a little bit different level than you've seen it before. So we're going to start off by defining the exponential function. So we're going to define it. And what that means is the exponential function has the form, or is of the form. And because we're calling it a function, we'll label it with an f of x. Again, that's the same thing as y. And we're going to do a to the x power. So something really momentous happens here. All of a sudden, the variable x is the exponent. So just as a word so that we're talking in the same language. So in this case, the base is a, and the exponent is your x. So just so you recognize that that's really, really different. That means all the rules that you know about how to work with expressions is thrown out the window, because all of a sudden it's not where it's used to being. We do have to have some restrictions on the base a. So we're going to say where the base can't equal 1, because if it were 1, it wouldn't be very exciting as a function, because it would be 1 to any power is 1. So it would just be a constant function. So the base can't be 1. And additionally, it has to be greater than 0. So we don't want a negative base, because a negative base would flip back and forth between positives and negatives depending upon the exponent. So we do have some restrictions. These are pretty important restrictions. They're going to come back and haunt us in the immediate future. So again, the base can't be 1, and it has to be a positive base. Okay. So then when you talk about these, let's talk about it from a graphing point of view, because I just think that's the easiest place to start. And to do that, we're going to build a table. So pretty much every textbook and every lecture I've ever done on this always starts off with the same exact graph. So we want to graph f of x equals 2 to the x power. So 2 to the x power. And to do that, we'll build a table. We'll build a couple of problems with tables, and then we'll step away from it. So here's f of x. And I'm going to plug in -2, -1, 0, 1, and 2. So those are the values we'll use and plugging them in. So normally I would start with -2, but I'm actually going to start down here just to make sure everybody understands what we're doing. So this would be 2 to the 0 power. That's this 2 raised to the 0 power. And does anybody remember what something raised to the 0 power is?
1.
Beautiful. So 2 to the 0 power is 1. And again, that's a reminder that a to the 0 power equals 1. Doesn't matter what the base is. Okay, well, 2 to the first power is easy. That's just 2. 2 to the second power would give us 4. So that makes perfect sense. So right now, this is what we know is going on. So we know at 0, we're up at 1. At 1, we're up at 2. And at 2, we're up at 4. So we can see it's definitely not a line. We can see a bit of a curve going in. But we need to know what's going on over on this side of the graph, and that's why we're going to plug in some negative values. So this is 2 to the -1 power, and a negative exponent moves it to the denominator. So that would be 1 over 2 to the first, which is just equal to 1/2. And does that make sense to everybody? So at -1, we're right there at 1/2. So again, what we're using is the fact that any number raised to a negative power is 1 over that number, the positive power. So you're not changing the power itself, only its sign. So what about -2 then? Well, that would be 2 to the -2, which is equal to 1 over 2 squared, which would be 1 over 4. So at -2, you're even closer to the axis. And there's a typical exponential graph, is what we're going to refer to it as. So this actually gets added into our toolbox of functions. So the x squareds, the x cubes, the absolute value of x's, you now have a to the x being added in. So an exponential graph looks like this. It should make sense that as you plug in larger and larger positive numbers, the graph is going to get more and more positive. It goes up really fast. This is what they call an exponential growth curve, which is what the COVID is doing right now. What about other characteristics it has? Well, is it ever going to drop below this axis? So in other words, can it ever go negative? Well, if I keep plugging more negative x values in, the fraction itself is going to get smaller and smaller and smaller, but it's never going to go negative. So that actually means that we have a horizontal asymptote sitting right on top of this axis. So right on top of this is a horizontal asymptote at y equal to 0. It does not have a vertical asymptote. It only has that horizontal asymptote. Okay, what about other characteristics? So let's talk about its properties or characteristics. So the properties of the exponential graph. So it definitely has a horizontal asymptote. In this case, it's at y equal to 0. That tells me what it's doing on the left side. It doesn't really tell me anything about the right side, but we know because it's an exponential, it just increases without bound. It is an increasing function. So increasing function. It will always be going uphill. It does have a y-intercept. And our y-intercept is at 0, 1. It has no x-intercepts. So until we start moving the graph around the system using transformations, it has no x-intercept at all. What about a domain? So what do you think its domain is? Well, in terms of our chart, can we plug in any x value we want? Well, sure, we can plug in any negative number. You can plug in any positive number. You can also plug in decimals. You can plug in fractions. You can do all kinds of things. You can plug in anything you want. So from the picture and from just pure logic, the domain is all real numbers. The range is where you have to be restrictive. We said that it's never going to go below this axis. So the range is going to start at 0 and go off towards infinity. And we'll use a parenthesis. You can't actually equal 0 on the exponential graph. Okay, those are your properties. So there are things to think about in our future. The other thing I would like to add in is notice that it is 1-to-1. So we'll say this is a 1-to-1 function. And why am I even bringing that up? Well, because we just got through doing it in section 6.2. And because it's 1-to-1, it will have an inverse that we'll talk about tomorrow. So it is a 1-to-1 function. Okay, let's do another one just to get some practice at it. Is everybody good? Looks like everybody's good. Okay. So now I'm going to change the base to a different base and we'll do it again. So let's graph f of x equals, I'm going to do 3 to the x this time, so 3 to the x. So in other words, what does changing the base do to the shape of that picture? We're going to actually plug in the same x and y values. So we're going to use -2, -1, 0, 1, and 2. Okay, so starting off with 3 to the -2, that would be the same thing as 1/3 squared, which would be 1/9, so fairly tiny. When I plug it in -1, I get 3 to the -1. That's 1/3 to the first, which is 1/3. 3 to 0, still equal to 1. Any number to the 0 power is 1. So we can see that this is going to be a fixed point for us. 3 to the first is going to give me 3, and 3 squared is going to give us 9. So, okay, so when I go to graph it, okay, so I have the point -2, 1, 9, so it's fairly close to the curve, or the axis. At -1, we're at 1/3, so still fairly close to the x-axis. We have the point 0, 1, we have the point 1, 3, and then at 2, we're clear up at 9. And once I have my 5 points in, I can come in and draw in my curve. And if you didn't have a scale showing you the tick marks sitting on there, you'd look at that and say, hey, that's the one we just graphed. It is. It's steeper on the right side because the base is bigger, and it gets closer to the x-axis faster on the left side because the base is bigger. But overall, it's got the same characteristics. It's still got that y-intercept at 0, 1. It still has a horizontal asymptote at y equal to 0. So sitting again right on top of that axis is a boundary line that we will not cross. It is a true asymptote. You still have a domain of all real numbers, and you still have a range that's from 0 to infinity. So basically changing the base didn't make a bit of difference to the overall picture or shape of that graph. So the bigger the base, the steeper it gets, but that's about it. Comments, questions? Okay, well, we said a few minutes ago that you can use any number you want as a base. So let's come in and do one more. So we're going to come in and graph y equals 1/2, the entire thing in parentheses, to the x power. So instead of using a base that's an integer value or a whole number, I'm going to use a fraction and see what happens. So we're going to pick 1/2. In terms of building our table, we're going to do the exact same thing. So we're going to use our -2, our -1, our 0, 1, and 2. So again, notice I'm just using the same points over and over again because it just really illustrates what's going on. So let's plug in the -2. So I now have 1/2 to the -2 power. Well, a negative exponent flips it. So that's going to become a 2 to the 2nd power. So I drop the negative on the exponent when I reciprocate or flip the fraction. That's a 4. When I plug in a -1, I have 1/2 to the -1. So again, the negative exponent is going to flip it. It becomes a 2 over a 1 to a +1, which is 2. 1/2 to the 0 power, still 1. 1/2 to the 1st power is 1/2. And 1/2 to the 2nd power, because they're single terms on the top and the bottom, you just square everything. So 1 squared is 1, 2 squared is 4. So, wow. So that definitely changed the location of our numbers. What is that doing to our picture? So at -2, we're going to be up here at -4. I'm sorry, +4. At -1, we're up at a +2. Still have 0, 1. But now on the right side is where we're going to get closer and closer to the axis. So the graph does something like that. Still have our horizontal asymptote sitting here. That's not changing. Still at y equal to 0. Notice the y-intercept is still at 0, 1. The domain would still be all real numbers. And the range would go from 0 to infinity. Okay, well, if we hadn't seen the actual numbers coming in, what we would notice is this graph compared to the 2 to the x graph that we graphed just a few minutes ago, which did this. So this was 2 to the x. This is 1/2 to the x. Those guys look like they're reflections of each other. They look like the graph has been flipped over the y-axis, which ties really nicely into doing the graphs with transformations. So unless it tells you to plot points, don't plot points. We're going to use transformations. So I'm going to backtrack and show you why this graph is a reflection of our initial graph. So I can rewrite that 1/2 as a 2 to the -x power. So in other words, I'm reciprocating my fraction, which introduces a negative on the exponent. So it's 2 to the -x. So I don't need the parentheses. I'm just going to write it as 2 to the -x. And now I notice the negative that we know is a reflection. So that negative is inside the function, which means it's a reflection over the y-axis. You're changing the sign on the x values, which flips it from left to right. So sure enough, it does exactly what we think it should do. It reflects over the y-axis. So once you hit past the tables, you can then come in and graph using transformations. So that's what we'll go from here. So unless you're asked to build a table, don't build a table. It's time consuming, you don't need it. So what I'm going to do is leave over here in the corner what we're going to call f of x equals a to the x. And again, I'm going back to a base of a because I don't want you to fixate on a number in that base spot. So that graph looks like this. It goes through the point 0, 1 and increases without bound. So this is the typical graph. It's domain and range. So regardless of the base, as long as it doesn't have a negative exponent, the graph is going to look like this. So we're adding this to our toolbox functions. This is now a toolbox function. So when you leave our class, we say, you know, all these graphs, these are the graphs you know. So now we'll graph using transformations. And it gets a lot quicker. So we're going to graph using transformations, and the first one we're going to do is f of x equals 2 to the x plus 1. And notice the plus 1 is written outside of the exponent, and that's how we know it's outside. So this is outside. This goes back into chapter 3, which has been a while now. But when you have a change that's outside, that takes the whole graph and shifts it how? Does anybody remember?
Up 1 on the y-axis.
Yep. Beautiful. We're going to shift up 1. Exactly what we're going to do. Okay, so what am I shifting up 1? Well, we only have 2 pieces of information here. We have this y-intercept. So the y-intercept that should have been at 1 is now going to be up here at 2. So this is now up here at 2. So that did one thing. The other thing that gets shifted is that asymptote that was at y equal to 0. So that asymptote is going to come up here to y equal to 1. And boy, if we were doing this where you were turning homework into me, I would really harass you about that asymptote. It needs to be in there because it's your boundary of where you're starting. So our picture would come in right above that asymptote, head through the intercept, and then head on up. So in terms of information, the domain is not going to change for the entire section. It's all real numbers. The range, though, is going to start at 1 and go off towards infinity. And again, don't include it as part of the range. And then we've already got the asymptote labeled, so the horizontal asymptote is at y equal to 1. So yep, you can take the picture and shift it up. You can take that picture and shift it down also. You can either go up or down. Does exactly what we expect it to do. Okay, well, what if we did f of x equals 2, and then inside the exponent, we're going to write an x minus 1. So 2 raised to the x minus 1 power. So this time, our change is on the inside. So that is happening inside the function. And if it's inside the function, we know it does stuff in the x direction. So how are we going to shift it this time? We got to guess.
To the right 1.
Yep. We're going to shift it right 1. So I'm going to go back to my base graph. Making sure I'm still on the board. The point that would have been at 0, 1 is now over here at 1, 1. So it takes the point that's the y-intercept and moves it to the right 1. It's not going to touch that asymptote, though. That asymptote, because you're not going up or down, is still going to be at y equal to 0. Okay. Then we'll come in right above the asymptote. We'll head to our point, and then we're going to head up from there. So it does change the y-intercept, but they're not asking for the y-intercept yet. We need a little bit more algebra behind us before we can go solve for that. Well, actually, you could solve for it. I'm sorry. You could. Couldn't you plug in a 0 for the x value? You'd get to the -1, so we know that's at a half. So you can find it. But they're not going to ask it. Okay, the domain is all real numbers. The range is still from 0 to infinity. And it has a horizontal asymptote at y equal to 0. Okay, so what we've already done is we've done up or down. We've done left or right. We did a reflection across the y-axis. The only thing left to do is a reflection across the x-axis. So what would that look like? So let's do g of x is equal to a -3 to the x. So the negative is on the outside because it's not trapped up there as an exponent. So this negative is outside. Okay, and because it's outside, we know it's a reflection over the x-axis. So if you stop and think about a negative x squared, it takes the parabola from opening up and opens it down. Same thing here. It's going to take what was up and flip it down. So our point that was at 0, 1 is now going to be down here at 0, -1. I call that my anchor point because it's where I'm anchoring my picture from. It's not going to change that asymptote. That asymptote is still right here at y equal to 0. But we're now going to start below it, head through the intercept, and then head on down. So the graph looks like that. We've taken what was up and made it down. So the domain is still all real numbers. The range, though, is going to go from -infinity to 0. So it does change that range around. But those are all the transformations. Now, in terms of stretching in the vertical direction, that comes from changing the base. So the bigger the base, the bigger the stretch, right? And so it doesn't really impact anything we're doing. You can't really see it on our pictures. So when we did our 2 to the x and the 3 to the x, they look very similar. So, okay, those are the transformations. And that's where the homework starts off. The next thing to talk about is a different number for that base, the base e. So the number e. So just like pi gets used a lot when we're talking about things that are circular, we have something called the number e that pops into this section, and we'll see it from here on out. Okay, and what e is it's an irrational number. It's a number that does not repeat in decimal form and does not terminate. What it actually is we're going to come in and define it. So the number e is defined as the number that the expression 1 plus 1 over n to the n power approaches as n goes to infinity. So in other words, this expression of 1 plus 1 over n to the nth power pops into the business world a lot. It pops into the biology world also. This is what we consider to be a growth of a true population. So as this value for n gets bigger and bigger and bigger, the result is that this expression is going to approach e. And just to help us out a little bit with this, oops, sorry, it's over here. If we build a table, and we're not going to do a lot of this, but you can go and do this on your calculator. So the value of n, and then that expression approaches. So when I talk about the expression, I mean this 1 plus 1 over n to the nth power. So if you let n equal 1, then that's easy to do. You'd have 1 over 1, which is 1. 1 plus 1 is 2. 2 to the first power is 2. So not very exciting. If you let it equal 5, then you get as a decimal 2.4883. So literally you're just plugging in a 5. That's 1/5. That's 1 plus 0.2 to the 5th power. But if you plug in 10, you then get 2.5937. If you plug in 100, so notice I'm letting my value of n get bigger and bigger and bigger, you get 2.7048. If I plug in 1,000, I get 2.7169. If I plug in 100,000, what starts to happen here is you see certain values. 100,000 was 2.7183. So you'll notice that the 2 was fixed. Now the 7 is fixed, and now you can see that the 1 is fixed. And then if you plug in 1 billion, that's 9 zeros, you'll see that the value is 2.7183, and then it goes on from there. So that's how we're going to define the number e. So e is approximately equal to 2.7183, and then we're going to do dot, 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 because it does go on forever. It's an irrational number. The pattern in here never repeats. So it doesn't terminate and it doesn't repeat. It is irrational. So it's just like pi. So pi's famous because everybody deals with it in elementary school when you start doing circles. But e doesn't really come into play until either high school or college. But it's also an irrational number. So, okay, well, what does that do for us? Well, we're going to come in and do one more graph of an exponential function. Okay. So let's graph. Oops. F of x equals e to the x. So we're going to come in and do the exact same values, -2, -1, 0, 1, and 2. And these are decimals, so this is e to the -2. And do you guys have your calculators handy or no? It's on your phone. So if you got your phone handy, you can do it. You will need to be able to find e on your calculator for the homework. So on the graphing calculator, you've got it in 2 spots. You have a key that says LN on it, and above that you'll see e to the x. So what you're going to do in order to figure out what e to the -2 is, you're going to come in and type in, you're going to clear, you're going to do second, and then type that LN key. And what you'll see on your screen is an e, and then you just need to give it the exponent, so then you type in -2 and hit enter. And if you do that, you get 0.135. Okay. Is everybody okay on where e is on their calculator or on their phone?
Yes.
Yeah.
Woohoo, yay. That's good. Okay, so then I'm going to fill in the rest of them just to save us a little time. So e to the -1 power was 0.367, 0.368 if I round. Anything e to the 0 power is going to be a 1. That's nice. E to the first power we said was 2.7183. E to the second power comes out to be 7.389. So, and then we're going to go graph it. And guess what? We're going to see the exact same shape that we've been seeing. So it's nice. It's just a different base. A little harder to graph if you ask me because they're decimals. So at -2, I'm at 0.1. That's really close to the axis. At -2, I'm at around 0.4, so not quite at a half, but almost there. We have 0, 1 again. At 1, we're up at 2.7, which is not quite 3. And then at 2, we're up at 7.3. So 4, 5, 6, 7, 8. So 7. Somewhere in there. So the graph looks exactly like we expect it to. And if we were to put this graph on the same grid as 2 to the x and 3 to the x, because this base is 2.7, which is between 2 and 3, you'd see this graph lies right between those two. So it just comes up really often in the business world and in the biology world for exponential growth curves. It still has a horizontal asymptote at y equal to 0. Domain is still all real numbers. And the range is still 0 to infinity. But now you can see what e is, and that it falls in the same kind of general category of an exponential graph. So again, we used a decimal as a base, we've used a fraction as a base, and we've used whole numbers as bases. So we've done all of that. It's really nice. Okay. We're getting there. We're almost there. Whew. It may not feel like it, but I'm throwing a lot at you today. Okay. So, the tail end of your homework has you solving some equations. So we're going to solve exponential equations. And what we're going to use is this fact that if a to the u equals a to the b, so I have a base raised to a u power, and that's equal to the same base raised to the v power, then u equals v. So what we're saying is if your bases are the same, then the exponents must be the same. So I'm going to write that in words. So this says, if the bases are the same, then the exponents must be equal. Exponents must be equal. So if the bases are the same, then the exponents have to be equal. So for instance, let's solve 2 to the x equals 16. So 2 to the x, excuse me, equals 16. Well, right now these bases are not the same. One side's got a 2, the other side's got a 16. So our goal is to make the bases into the same number so I can use this rule. So always work in general with the larger side because it's a lot easier to make it as the other number versus taking the 2 and trying to write it as a 16. So we know, let's see, that 2 squared is 4, 2 to the third is 8, 2 to the fourth, sure enough, is 16. And if you don't know that, you sit there and play on your calculator, taking the base and raising it to successive numbers until you get to 16. So we're saying that 2 to the x is equal to 2 to the 4. So I'm rewriting the 16 as a base of 2. The minute I do that, because the bases are the same, I can then come in and set those exponents equal, and I'm done. X is equal to 4. So we just solved our first exponential equation. Yay! I don't know if that was impressive to you, but I think it is. So, okay, let's do a little bit more complicated one. Let's solve 2 to the 2x minus 1 equals 4. So 2 to the 2x minus 1 equals 4. So again, I have the same issue. One side's got a base of 2, the other side has a base of 4. I need them to be the same numbers. Well, we can rewrite that 4. So 2 to the 2x minus 1 equals 2 squared. So again, I'm not touching the left side, I'm only manipulating the right side. 4 is 2 squared. The minute you have those bases as the same numbers, you can then set the exponents equal. And then we'll solve. So we can add the 1, we'll get 2x equals 3, and x equals 3 halves. So we get an answer. You can check these. Because you're solving, you can check them. So you can come in, plug that 3 halves in as the exponent. 2 times 3 halves is 3. 3 minus 1 is 2, and 2 squared, sure enough, is 4. So you can check them because you're solving them. So comments or questions so far? They're going to try and be a little sneakier, so be careful. Don't let them. So we have 1/5 raised to the x, and that's going to be equal to 1 over 25. So 1/5 raised to the x, notice it's in parentheses, is equal to 1 over 25. So you have a couple of ways of doing this. I tend to not like to work with fractions. So the first thing I'm going to do is take that left side and make it into 5 to the negative x. On the right side, I'm going to make that 25 to the negative 1. And that just gets rid of the fractions. You may not like to do that because you don't like negative exponents, but we can deal with those. And then we're going to recognize that 25 is the same thing as 5 squared. So that's going to be 5 to the negative 2 equals 5 to the negative x. We finally have the bases the same. So negative x is equal to negative 2. And x is equal to 2. And you may have seen that right back up there. Just depends on how much you want to process things. So. Okay, and to get a little bit more complicated, what if we have 8 to the negative x plus 1, oops, sorry, 14, negative x plus 14 is equal to 16 to the x. So 8 raised to the negative x plus 14 is equal to 16 to the x. Okay, well, unfortunately, there is no way to rewrite 16 as a base of 8. It isn't. So I know that 8 times 2 is 16, but that's a multiplication. It's not a power. So what we're going to do is recognize that both 8 and 16 are powers of 2. So I'm going to break them both down. So this is 2 cubed, the negative x plus 14. And on the other side, we saw earlier that that was 2 to the 4th times the x. So notice how I did this. When I rewrote this as 2 cubed, I immediately put the exponent in a set of parentheses. And on the other side, I kept that exponent up there by the 4. Because when you raise a power to a power, you multiply, which is what we just did. Okey-dokey. We're going to keep the 2 to the 4x on that side. On this side, let's go ahead and distribute in our 3. That would be a negative 3x. And 3 times 14 is 42. Since the bases are both 2's now, we can drop those 2's out of there and set those exponents equal as 3x plus 42 equals 4x. I'm going to add the 3x to the right side and get a 7x. On the left side, we'll keep the 42. Dividing it out, we'll see that x equals 6. So even though it looked kind of weird at the beginning, right, we know that x equals 6. And you could check it on your calculator. You can take 16 to the 6th power. You can plug the 6 in over here, and you'll get 8 to the 8th power, and they should be equal to each other. So, okay, and those are exponential functions. So, any comments or questions?
No, I'm good.
Yeah, everybody, you've seen these
Good,
before.
yeah.
They may be a little more complicated, but are we good? Okay, again, if
Yeah.
you didn't send me your scratch work from the exam, please send that to my Gmail account immediately, please, so I can get those exams graded. And then I'll try to get them into Blackboard. But you can go into Pearson and see how you did on it. So, Rich, I got yours graded. Matt, I sent you an email back, and I got yours graded. So, you can see what your grade currently is. So, hey, have a great day. Enjoy it. We'll see you tomorrow. Any questions?
Nope.
No. Okay.
Nope.
Have a good one. Bye-bye.
Bye.